Welcome to a journey into one of the most startling environmental discoveries of our time. For generations, we've viewed Earth's pristine white glaciers as the last bastions of untouched wilderness, places beyond human reach. Today, we'll explore how that perception has been shattered by groundbreaking research revealing microplastics embedded in ice cores from the most remote glaciers on our planet. Join us as we uncover how these frozen archives are telling the story of humanity's plastic footprint, how these pollutants travel through our atmosphere to reach seemingly untouchable places, and what this means for our planet's future as these glaciers begin to melt. Our story begins with the groundbreaking study published in the Journal of Glaciology that has fundamentally altered our understanding of pollution's global reach. Led by glaciologist Dr. Mei Zhang from the Cryospheric Research Institute, researchers have discovered microplastics, tiny fragments less than 5 millimeters in size, embedded in ice cores extracted from some of Earth's most remote glaciers, including those in Antarctica and the Tibetan Plateau. This isn't just another pollution story. It's a revelation that nowhere on Earth remains truly untouched by human influence. These glaciers, once symbols of pristine wilderness, are now revealed to be unintentional archives of humanity's consumption patterns stretching back decades. The ice cores contain layers of accumulated snowfall that have compressed into ice year after year, each layer capturing the microplastics present in the atmosphere at that time. This chronological record offers unprecedented insights into the temporal and spatial dimensions of this modern contaminant, effectively creating a timeline of our plastic usage preserved in ice. The Guliya ice cap on the Tibetan Plateau seems like the last place one would expect to find evidence of human pollution. Located at elevations exceeding 6,700 meters and hundreds of kilometers from major population centers, this remote location was thought to be beyond the reach of direct human contamination. Yet the meticulous extraction and analysis performed by Dr. Zhang's team revealed a disturbing progression of plastic contamination in this inaccessible region. The data shows an approximately 40-fold increase in microplastic concentration since the 1960s, directly coinciding with the global boom in plastic production and consumption. To identify these pollutants, the team employed cutting-edge spectroscopic techniques that allowed for precise identification of polymer types, particle sizes, and even degradation patterns. These details provided crucial information about the particles' origins and how long they had been suspended in the atmosphere before being deposited in the ice. The precision of their findings transformed our understanding of pollution's reach and established these glaciers as natural historical archives documenting humanity's accelerating relationship with synthetic materials. What makes these glacial records particularly valuable to environmental scientists is their chronological precision. Unlike ocean sediments or soil deposits, which can be disturbed by biological activity or physical processes, glacial ice in stable regions accumulates in distinct annual layers. Each year's snowfall compresses into ice, trapping atmospheric particles and creating a time capsule of environmental conditions. This stratification allows researchers to correlate specific ice layers with historical events and production trends with remarkable accuracy. The research team identified distinct signatures of industrial polymer innovations throughout the ice core. A layer from 1979 contained the first appearance of polycarbonate particles, matching exactly when this material began mass commercial production. Similarly, distinctive fluoropolymer particles appeared in layers from the mid-1980s, tracking perfectly with their industrial adoption timeline. The team also documented a notable spike in polyethylene terephthalate (PET) particles in ice layers from the mid-1970s, corresponding with the introduction and rapid adoption of the first PET beverage bottle. Microfibers from synthetic clothing showed marked increases in ice layers from the early 1990s, coinciding with the global fast fashion boom and widespread adoption of polyester fabrics. This temporal precision transforms glaciers into natural historical archives with a clarity unmatched by other environmental records. Perhaps the most surprising aspect of these findings concerns the complex atmospheric pathways that transport microplastics to remote glacial environments. Before this research, scientific consensus held that microplastic pollution primarily spread through ocean currents and directly contaminated waterways. Dr. Zhang's team has documented that high-altitude wind currents can carry microplastic particles thousands of kilometers from their source, effectively creating a global distribution system for these pollutants that reaches even the most isolated regions of Earth. The research identified a previously undocumented phenomenon termed plastic precipitation, wherein microplastic particles serve as nucleation sites for ice crystal formation in high-altitude clouds. This process significantly accelerates the deposition of these particles onto glacial surfaces through wet deposition, precipitation, and dry deposition, direct settling. Using advanced spectroscopic analysis combined with atmospheric trajectory modeling, the research team determined that approximately 73% of the microplastics found originated from packaging materials, with the remaining portions comprising textile fibers at 14%, tire wear particles at 8%, and various industrial polymers at 5%. As Dr. Zhang noted, what we've essentially uncovered is that the atmosphere has become a global conveyor belt for plastic pollution, depositing human-made particles in locations humans have rarely even visited. This atmospheric transport mechanism means no environment on Earth remains truly pristine anymore. The research team's findings revealed something even more concerning: the existence of atmospheric microplastic hotspots, regions of the upper troposphere where convergent air currents create unusually high concentrations of suspended plastic particles. These hotspots appear to form predominantly over regions with specific meteorological conditions, including the jet stream boundaries and areas of persistent high-pressure systems. The team documented one particularly significant hotspot over Central Asia that appears to be a primary source of microplastic deposition in the Himalayan region. What makes these hotspots especially problematic is the extended atmospheric residence time for microplastic particles. The smallest fragments can remain suspended in the atmosphere for weeks or even months, allowing for truly global transport. This means that plastic pollution from one continent can easily be deposited on another, creating a worldwide distribution network for these contaminants that knows no boundaries. The implications are profound. Plastic waste management is no longer just a local or regional issue, but a truly global environmental challenge that requires coordinated international response. Beyond serving as a historical pollution record, these findings have significant implications for climate science and glacial dynamics. Dark-colored microplastics alter the albedo, or reflectivity, of glacial surfaces, potentially accelerating melt rates through increased absorption of solar radiation. Through controlled experimental plots on the Guliya ice cap, the research team measured this albedo reduction effect directly. Their preliminary calculations suggest that in heavily contaminated areas, microplastic deposits may increase melt rates by up to 2.8% annually. While this might seem like a small figure, it compounds dramatically over decades and could significantly advance the timeline for glacial retreat in affected regions. This creates a troubling feedback loop. As climate change causes more glacial melt, more microplastics are released, which in turn causes more melting. Furthermore, as these glaciers melt, they release stored microplastics into freshwater systems, creating what researchers describe as a secondary contamination event, decades after the original pollution occurred. This time-delayed release means that even if plastic production ceased entirely today, glacial meltwater would continue introducing microplastics into downstream ecosystems for centuries, creating an environmental legacy that will long outlast the glaciers themselves. Contrary to popular perception, glacier surfaces are not biologically inert. They host diverse communities of extremophile organisms adapted to survive in these harsh environments. These communities include specialized bacteria, algae, fungi, and microscopic animals that form the base of unique food webs. The most recent and perhaps most concerning component of Dr. Zhang's research examines how these glacial organisms unexpectedly interact with the introduced microplastic particles. Several species of cryophilic, or cold-loving, algae that form colored blooms on glacier surfaces have been observed incorporating microplastic particles into their cellular structures. This represents one of the first documented cases of microplastic bioaccumulation in such extreme environments. Electron microscopy revealed that particular algae species appear to be adapting to use these synthetic materials as substrate, with some colonies showing higher growth rates in plastic-rich areas of the glacier. Genetic analysis of these organisms revealed the emergence of novel enzymes capable of metabolizing specific polymer components, suggesting rapid evolutionary adaptation to these new environmental constituents. As microbiologist Dr. Soren Christensen, a co-author of the study, explained, what we're witnessing is evolution in real time. These organisms adapt to pollutants that didn't exist in their environment until very recently, geologically speaking. The implications for freshwater ecosystems worldwide are just beginning to be understood, but they suggest profound changes to the base of aquatic food webs that could reverberate through entire ecological systems. As glaciers melt, they don't just release water. they release everything stored within their ice, including decades of accumulated microplastics. The research team has launched a comprehensive follow-up study examining how these microplastic-adapted organisms affect downstream ecosystems as glacial retreat accelerates. They've already detected modified algal communities containing embedded microplastics in rivers up to 400 kilometers from their glacial sources, indicating how far-reaching these effects can be. This raises urgent questions about the potential impacts on downstream ecosystems, drinking water supplies, and eventually marine environments. Many major river systems in Asia, South America, and other regions rely on glacial meltwater, especially during dry seasons. These rivers provide drinking water for millions of people and support agricultural systems that feed billions. The potential for microplastics to enter these critical water supplies represents a significant public health concern that we're only beginning to understand. Additionally, as these plastics and plastic-adapted organisms make their way downstream, they may introduce novel compounds and biological communities into ecosystems that have never encountered them before, potentially disrupting established food webs and ecological relationships that have evolved over thousands of years. The chronological precision of ice cores provides environmental scientists with an unprecedented opportunity to correlate specific plastic pollution patterns with global production and consumption trends. Beyond just measuring quantities, the research team documented several distinct plastic horizons in the ice record that align precisely with major developments in consumer products and industrial practices. These frozen layers tell the story of our changing relationship with plastic materials with remarkable clarity. For instance, the appearance of specific polymer types in the ice record perfectly matches their introduction to consumer markets. The research effectively creates a timeline of humanity's plastic consumption preserved in ice, from the early adoption of basic polymers to the complex blend of synthetic materials we use today. This chronological record serves as both a scientific resource and a powerful reminder of how quickly our use of synthetic materials has escalated. In just a few decades, plastics went from revolutionary new materials to ubiquitous pollutants found in the most remote places on Earth. The ice cores reveal that our plastic footprint has grown exponentially rather than linearly, with each decade showing significantly higher contamination levels than the last, mirroring the acceleration in global plastic production and disposal. The discovery of microplastics in remote glacial ice represents far more than another data point in our understanding of pollution's reach. It fundamentally alters our conception of environmental contamination as a spatially and temporally bounded phenomenon. These findings reveal plastic pollution as a global process that transcends geographical barriers through atmospheric transport and transgresses time through glacial storage and delayed release. These glacial records serve as physical archives of the Anthropocene, tangible evidence of humanity's capacity to alter even the most remote environments on Earth. They challenge us to reconsider our relationship with synthetic materials and recognize that in a world of global atmospheric circulation, no isolated environments are immune to human influence. The microplastics frozen in these ancient ice sheets tell a story of unintended consequences that will continue to unfold long after the ice disappears. The research from Dr. Zhang and colleagues offers a powerful reminder that environmental systems are interconnected across space and time in ways we are only beginning to comprehend. Plastic products manufactured decades ago continue their environmental journey today, and those produced now may impact ecosystems centuries into the future. This temporal dimension of pollution presents unique challenges for environmental policy and remediation efforts, as it requires addressing not only current production practices but also the legacy effects of past consumption patterns. The discoveries made by Dr. Zhang's team wouldn't have been possible without significant innovations in research methodology and analytical techniques. Extracting and analyzing ice cores from remote glaciers presents enormous logistical and scientific challenges. The team developed specialized drilling equipment that minimized contamination risks, a critical concern when studying microscopic particles. Each ice core was extracted with extraordinary care to prevent modern plastics from contaminating the samples. The cores were transported in specialized containers and processed in ultra-clean laboratory environments where even the air is filtered to remove potential contaminants. The analytical techniques employed represent the cutting edge of environmental science. The team used advanced spectroscopic methods including micro-Fourier transform infrared spectroscopy and Raman spectroscopy to identify specific polymer types at the microscopic level. These techniques allowed them to distinguish between dozens of different plastic varieties and even identify additives and degradation products. They combined these analyses with advanced atmospheric modeling, using supercomputers to track how air currents could transport particles from source regions to deposition sites. This interdisciplinary approach, combining glaciology, atmospheric science, chemistry, and computer modeling, exemplifies how modern environmental research increasingly requires collaboration across scientific disciplines to understand complex global processes. As climate change accelerates glacial melt worldwide, we face the prospect of these frozen repositories releasing decades of accumulated contaminants into freshwater systems that often serve as drinking water sources for millions of people. This research fundamentally changes how we must think about plastic pollution, not as a problem confined to visible litter or ocean gyres, but as a truly global phenomenon that reaches the most remote environments and persists across generations. The findings demand a reevaluation of how we approach plastic production, usage, and disposal. Traditional approaches focusing solely on waste management and recycling fail to address the atmospheric transport mechanisms that distribute microplastics globally. The research suggests that even areas with excellent waste management systems contribute to worldwide microplastic pollution through atmospheric release. This calls for more holistic approaches that consider the entire life cycle of plastic products, from production to disposal, and acknowledges their potential for global distribution. The temporal aspect is equally important. Plastics entering the environment today may continue to circulate and impact ecosystems for centuries. This intergenerational dimension of plastic pollution presents ethical questions about our responsibility to future generations who will inherit the environmental consequences of our consumption patterns. The research serves as a powerful reminder that in our interconnected Earth system, there are no truly isolated actions or environments. What we produce and consume here today may end up preserved in ice on the other side of the world tomorrow, creating an environmental legacy that outlasts us. The discovery of microplastics in Earth's most remote glaciers represents a pivotal moment in our understanding of humanity's environmental impact. These frozen records reveal that no corner of our planet remains untouched by human influence. Our plastic footprint has reached places we ourselves rarely visit. Through atmospheric highways, our discarded plastics travel thousands of kilometers to settle on pristine ice, creating a chronological archive of our consumption patterns that spans decades. As these glaciers now melt due to climate change, they release these stored pollutants into water systems that sustain millions of lives, creating a secondary wave of contamination. Perhaps most remarkably, we're witnessing evolution in real time as glacial microorganisms adapt to incorporate these synthetic materials, potentially altering fundamental ecological relationships. These findings transform how we must think about environmental contamination, not as isolated incidents in specific locations, but as interconnected processes that transcend both geographical boundaries and time. The microplastics frozen in ancient ice tell a story that will continue to unfold long after the glaciers themselves have disappeared, challenging us to reconsider our relationship with synthetic materials and recognize the truly global and intergenerational consequences of our consumption choices. In the layers of ice from the roof of the world, we've discovered not just pollution, but a profound message about our responsibility to the planet and to future generations. Thanks for watching. Please like, subscribe, and hit the bell icon for updates. Your feedback is appreciated. We hope to see you again.